Continuing from the from lecture two, the layering and protocol stacks. So as we mentioned, 7 layers of the open system interconnections model, and we just want to go through all of them and see uh, what kind of roles they play, the kind of tasks that each of those layers have been assigned to do or to handle in terms of how information is carried through network devices, through a network topology, from a sending point to a receiving point or to a receiving node. Okay, so if I'm not mistaken, we got to um, the network layer. We were able to cover the physical layer and then the data link layer. So now let's move on to the network layer. The network layer is responsible for end-to-end packet delivery. Uh, so as I mentioned earlier in the second lecture, when it comes to the data link, it's all about the frames, handling frames, and the physical layer is all about the bit sequence. The bits that are used to form the binaries. You know. And then now at the network layer, it's more about the end-to-end delivery, or the end-to-end of packets deliveries. So here we're focusing more on packets from the original source to destination. Um, there's obviously two devices that needs to be attached together on separate networks to make that possible, obviously. So from the sending point to a receiving point, you do need two network devices to absorb that end-to-end packet delivery. Okay, and this is where routers play a key role in handling um, that end-to-end packet delivery. So you do need two devices attached to different networks to allow the network layer to function, um, or to handle its task. Um, so by definition, the core duties of the network layer revolves around logical addressing. So it is where IP addresses, which happens to be, logical addresses. Unlike the data link, it was more the physical addresses or the MAC addresses. At the network layer, it's more about the logical addresses, which is where IP addresses comes into play, which we'll cover intensively later on in uh, subnetting, the IP address subnetting. And then another duty is routing of the packet. Since it's an end-to-end packet delivery, there has to be a way for the packets to be, um, sorry, this is an end-to-end packet delivery, which involves uh, two devices across, send information across different or attached to different networks. Then obviously you have to um, uh, incorporate some kind of way of making sure the devices know which path to take to deliver the message. And that's where routing comes into play. So routing plays a key role here. And then also switching, also a bit of switching in here as well. And then congestion controls and your quality of service is also um, key essence over here. Okay, so yeah, end-to-end packet deliveries and two devices attached to different networks. Key duties: logical addressing, routing, switching, congestion controls, and quality of service. So if you want to look at this from the uh, The delivery point again, like the way we did it for the data link as well as the physical. So in this case, you're gonna have three layers now, right? And let's look at how they work in terms of delivering a message. So here you notice that now you do have one more layer attached. Okay, so this is where the information picks up IP address and then hands off to the data link before the physical link, and then obviously via some kind of medium where those bit streams of bits are converted into either digital signals or analog signals. And then the first node or the first intermediate systems, which happens to be a router in this case, would have to, obviously it's always going to be a router, would always have to, uh, uh, pick up the message first, and then to be able to identify the destination address, the message has to go through the physical layer, through the data link layer, and then hit the network layer for it to identify uh, the the destination address, and that's needed for the device to be able to figure out which route the message needs to take to get to its final destination. So in this case, assuming that the message was destined for or destined to end system F, then obviously when it gets here, the message the message reaches this point over here, it's up to the router to identify which route, because you do have two routes that are attached to it or that are acting as link to it. So it has to figure out which route contains the destination address or destination node, and then when it does figure that one out, and that's one of the key reasons why the um, the message has to climb all the way up to the network layer, so that that address, that destination address, can be picked up, and then routing is determined uh, to determine which path the message needs to take, and then it goes through the same process all the way until it gets to the final end system. Okay, so quite an interesting way of going about it. It's not that interesting; it's just more or less a structured task for the system, especially when it comes to network systems. It needs to be structured. Otherwise, we don't want issues. We don't want some of the um, issues that relates to packet deliveries, flow control, uh, throughput, and all of that as a challenge here. Delays, latencies. We're trying as much as possible to avoid that, and that's where some of these key protocols play a key role at the various layers. Okay. So once again, it's also one of the key reasons why the layers were designed to make sure we're able to make sure we meet our uh, key delivery services or delivery address our key delivery challenges. Yes, we're to address some of those. Okay, so it goes through that process until the final destination is the message is delivered to. Okay, another example of that is the same process where you do have the message going through this route over here. So in this scenario, you have the message going through a bus line before it hits the router, and then the router, uh, and then it goes through a ring. So here you combine how many two topologies? We have a bus topology, a ring topology, and a bus. So two topologies are being used here. In this case, it could be fiber optic transmission or fiber optic implementation. So we see how the network layer also act in terms of making sure the message is delivered to the right destination. Okay, so in that sense, we could say that the network layer is responsible for the delivery of individual packets from source host to destination host. Yeah, and then one thing I should probably point out is that within this, the packets actually are individually passed through different, or the path, the message or the packets, breaking it into individual pieces, can take various routes towards its destination. Assuming we had multiple routers here or multiple routes for the information to be transmitted, then it is the job of the routers, which are the intermediate systems, to decide how the those individual packets needs to be forwarded, especially uh, if time and and network congestions or network challenges are a huge problem. It's up to the router to figure out how to address some of those issues to be able to deliver the message successfully. So in that sense, the routers can forward the packets through different routes. So on a bigger network, not something like on a bigger network, then the packets can take different routes as long as they do have a way of finding its final destination at the other side of the destination point or at the receiving end. Okay, that's what we summarize it by saying that network is responsible for delivery of individual packets from source host to destination host. Because we know the reason the word individual packets are there because the packets can take different routes, especially when it comes to the network layer, and it's up to the packets to it's up to the routers to regroup the packets that has been sent to various routes when it finally gets to the point of its delivery. Okay, before I hand it over to um, the receiving node. Okay, very good. I think we'll see that in some of the demonstrations when it comes to the design implementations. Well, I'll probably put together a much more elaborate network um, with multiple nodes, multiple routes for the message to go through. And then you kind of figure out how a router is able to manage individual packets being sent through various paths, but ultimately will finally get to its final destination. Okay, so that's more or less uh, the the summary, as we can point out, as what the network layer is responsible for delivery of individual packets from source host to the destination host. The next layer is a transport layer, which is the fourth layer. So the transport layer handles most of your processes or process to process delivery, unlike the network, which handles packet to packet deliveries. And then the data link is more about the frame deliveries. The transport layer is more in charge of the process to process. So processes uh, in terms of port addressing, segmentations, and reassembling, how to address congestion controls and flow controls are all some of the key things that revolve around process. So we say process to process deliveries are the one of the key uh, responsibilities of the transport layer. So yeah, it delivers most of the process to process uh, transmission for entire messages, which is from source to a destination. And also, it's needed when several processes are running um, actively at the same time. It's the job of the transport layer to be able to manage some of those processes that are multiple processes or several processes that are ongoing at the same time. So key tasks in terms of process to process, you'd have port addressing, segmentation, reassembly, congestion controls, flow controls, error controls, and what have you. So here's a diagram of how some of these managed at the transport layer before they actually get handed over to the network layer. So you do have your segments of the data with their various headers, which contain the addresses of destination and source address as well, being grouped into various segments to be able to manage the process-to-process deliveries. Okay, before it gets handed over to the network layer, and a reverse format when the message is going to the destination end. Okay, so this is more or less like going from the machine at the application layer, from the application, which is the seventh layer, all the way down. And then this is more of the reassembling back to the application when it gets to the destination. So you are from here from source and then from here to destination. So hence the arrows moving down and here the arrows are moving up. Okay, so another level of that, network layers and host to host delivery point, and as well as the transport, which is process to process delivery of reliable messages across. So generally, from this, we can state that we can also say that when it comes to sessions, it's more responsible for the uh, dialog controls and synchronization of process-to-process delivery of messages from source to destination. That's how we can summarize that in a way. So it's responsible for the delivery of messages from one process to another. Okay. Oh, sorry. So I was talking about. So I meant the transport layer is responsible for. So from this, we can summarize what the transport layer does by saying that it is responsible for delivery of messages from one process to another. I was mentioning dialogue, controls, and synchronization, but that applies uh, to the next layer, uh, which is more or less the session layer. Okay, so let's try to get to that part and see. So this is purely for this is at the transport layer. So that's where you have to. That's where we summarize our transport layer as more or less responsible for delivery of messages based on processes. Okay, as we mentioned earlier on over here. Okay. And for session, which I was trying to put across, I wish I was using as the transport. That session, which happens to be a layer 5, it's more responsible for the dialog controls and synchronization of the message. After it's been separated to segments at the transportation layer. So this is how we just summarize the session layer. I do have a video that you guys are going to be watching later on the OSI model using some animation. Okay, well, based off animation, so you can have an idea of how some of these layers play a key role in delivery of messages. Yep. And then from the session layer, you move on to the presentation layer before the final application layer. The presentation layer is more responsible for the translation of as well as compression and encryption of the message. So in terms of security and sizes of the message and how you actually translate it from one form to another, it's a sole responsibility of the presentation layer. So the presentation layer is responsible for translation, compression, and encryption of the message. And then finally, we move on to the application layer. Application is the seventh layer. Um, that's where we look at how most of your services, your application services are well managed. Uh, so in a way, you can put it across by saying that the application layer enables users to actually access the network, and services that it provides to the networks includes emails, especially from the users into the network. So services provided to users through the network, through the access of the network, emails, uh, remote file access and transfer, which revolves around Telnet or FTPs, as well as your World Wide Web, your internet websites or web pages or your web addresses. So those are the applications. So most of key applications falls within the application layer. Obviously, the name application layer states that, so you can easily tell that it's the sole job of the application layer. If you're dealing with anything that revolves around application, then you know for a fact that it's going to be handled by the application layer. And that's usually always the first point, especially when it comes to how the information actually gets handed down until it hits the first layer, which is the physical layer, before it gets sent out over a medium. It's obviously the starting point. So you can tell the uh, um, applications from various devices that end users have access to and uses to address most of their computing needs, uh, all would fall within the application layer. Okay? Great. So in summary, the application layer is responsible for providing services to users as well as to the network, because enables users to access networks. All right. So when the application layer provides a service to the user, users are able to gain access. It helps users are able to use the network to help them transmit their services down through the network. Okay, we good on that? So I don't know. Yeah, so it's the summary. It's like the application layer is responsible for providing services to the user, and by that, as I was mentioning, uh, the network plays a key role in terms of how users access the services. Okay, so a good way to more or less remember the OSI model, which is a convenient aid for remembering the OSI layer names, is to use the first letter of each word in a phrase. And uh, so, so one of the phrases that some people use is, all people seem to need data processing, where you say that the all starting with A is the application, people, P having a presentation, seems as having session, T two for transport, and then N need, and for the network, and then for data part, D stands for the data link. And when it comes to processing, P goes with the physical layer. So all people seems to need data at some point, I guess. So to summarize the layers and their protocols, we say that the application layer is designed to allow access to the network resources, whereas the transport, sorry, so we're just kind of grouping this here. The transport delivers, um, provides, so sorry, the transport provides reliable process-to-process message delivery and error recovery. And then when it comes to the network, we talk about more or less moving packets from source to destination, and also provide inter-networking as well. And then data link handles the organizations of bits into frames to provide hop-to-hop deliveries. And finally, the physical handles the transmission of bits over a medium so as to provide the mechanisms or the mechanical and electrical specifications required for those bits to be carried on through a medium en route to its final destination. Okay. So lower level protocols, which defines the electrical and physical standards to be observed, bits and bytes ordered, and the transmission and error detection, as well as the correction of the bit streams, are very, very essential, especially at the lower level. So basically, we're just saying that uh, at the lowest level, um, electrical and physical standards needs to be observed. That's where we talk about bits and bytes in ordering them in the right order, on the right, uh, frame, or in the right sets that it came in, to be able to address, uh, the delivery issues, which address the delivery issues in terms of reliability, and the transmission and error detection, as well as the correction of the bit streams, are very, very key. So they are more or less being handled at the lower level protocols. So we're talking about key protocols that can be summarized over here are more of the low level protocols, and the high level protocols, which are more of the app protocols. So from layer 3 all the way up to the seventh layer, we're talking about the high level protocols where we're dealing with data formatting, the syntax of the errors, termination of the computer dialog, character sets, sequence of delivery of messages, and what have you are all handled at the upper levels. Um, I guess you could say the first three is actually more or less the low level, since network also deals with more of the logical addressing part. So yeah, so the first three are more of the low levels, and then from 4 all the way up to 7 handles more of the high level protocols. Okay, to summarize that part of the uh, layers and their protocol stacks. Now let's talk about the TCP/IP protocol power model. This is more of the uh, this is more of the OSI models, right? And we did mention that there are actually two types of model, if you remember correctly, from our lecture two. Sorry, so that's we had the OSI model, and then we did have the TCP/IP model as well. Now let's look at that also, but we'll see what kind of arrangement that also has, if the same as the OSI model, or also the change if you have a different form or different format in terms of layering orders. Okay, so with the TCP IP, there's a bit of a change. Yeah, it was more or less designed to handle or to be broken into four main parts, where the same OSI model are grouped. Some of the various layers within the OSI model are grouped into just one uh, layer instead. Okay, and then the others are also grouped to form a different name or what have you. So with the TCP/IP, the first three layers are usually considered as the application layer. So we have application, presentation, and session would form the application layer within the TCP/IP. And the second layer will be the transport layer, which is solely a transport. And when it comes to the network, uh, it's usually interpreted as the internet network layer. And then we do have um, the data link, and then the data link and the physical link being classified as more or less host to network layer. Okay, so let me show the diagram over here. Here we go. So yeah, the first three layers are grouped as applications, whereas the transport is left alone to handle most of the transport needs. And the network also has its own, whereas the final two, data link and physical, are more grouped under the host to network layer. Okay, and we do have some of the protocols that you would find within some of these layers, especially in the TCP/IP. TCP/IP here is the transmission control protocol. So anything that relates to transmissions, protocols are more handled. So you're looking at SMTPs or simple message transmission protocols, FTP for file transfer, um, and HTTP, your hypertext, DNS, domain name services, simple network management protocol, telnets, SCTPs, TCP, UDPs, user datagrams, transmission, secure connection transfer protocols. Um, and then for the network part, you have your ICNPs, IGNPs. We'll cover some of these at Datacom 2, by the way. And then ACKs and the RACs as well for the networks. Okay. So one key thing that always comes that kind of unifies or more or less uh, sticks out when it comes to the OSI model as well as the TCP/IP is addressing. And as you know, we do have physical addresses, logical addresses, port addresses, and very specific addresses. So that makes it about 4 level of addressing that needs to be observed, especially when it comes to message delivery. Okay, and also process delivery, messages and process delivery. So we want to look at some of those because the key is essential. They're very essential, or they're key information or uh, key um, uh, a unique task or unique process or protocols that's either both either TCP or OSI that has to observe, especially when you're relating to information delivery from a source and to a destination. Okay. Now let's look at the addresses. So we do have the 4 level of addresses: physical addresses, logical addresses, port addresses, and other specific addresses. Um, when it comes to the relationship of layers and addresses within TCP/IP, you notice that there's a bit of a formatting change, especially at the TCP/IP level. So key reference here when it comes to the application layer of the TCP/IP, the kind of address that we look at is at the process level is more of the specific addresses. Okay, so we're looking at specific addresses that are attached to key processes that have been handled at the application, presentation, and session level. Okay, so this is where session IDs and what have you are incorporated within the all called upon, especially at those process levels, and hence we have specific addresses. But when it comes to the transport layer, it's more of the ports because we're talking more or less about sockets and how they handle these transmissions. So various socket numbers, which in this case are called port numbers are more of the key reference here when it comes to the transport layer. But for the network, it's purely the logical addresses where IP addresses play a key role. And then when it comes to the internetwork part, which is the data link and the physical layer, it's more about the physical address or MAC address in a sense. So the 4 addresses that we kind of like mentioned over here, this is how they group when it comes to the TCP/IP uh, level in terms of its relationship. Okay, let's keep this in mind whenever you're trying to relate addresses to the various layers within TCP/IP application, where you focus more of the process at the application, presentation, and session level. We're talking more of the specific addresses. Okay, that's where they play a key role at. And then when it comes to transport, it's purely the port addresses. Okay, and network is more of your logical addresses with IP address as center point. And then for the last two, it's more of a physical addresses where MAC is, is the key focus. Okay, great, that's wonderful. So we got all that. So in general, you can say physical address. If you want to talk about physical address, will change from hop to hop. So in this addressing levels, we can say physical addresses actually do change from hub to hub because they're being handled uh, on various mediums or they're going through various devices, which is either uh, a router or a switch or a hub or whatever, access points, and all of these, and even media cards, network media cards as well. So at those levels, they bound to be changed, especially at the very moment the message leaves one device, then the next device that they encounter would have to take on its uh, physical address. So that's what we say physical addresses will change from hub to hub. But when it comes to logical address, they do not change. IP address do not change, especially with the public ones, because they are needed for the to route the message from a source point to destination. It's able to, that's what is needed to address where the message actually needs to go to. So those do not change. Okay, it's kind of like house addresses; they don't change. They're always going to be fixed, mostly for the purpose of routing and information delivery. Okay, so logical address remain unchanged usually. Okay. We'll look at situation where they might change, but actually not changing. That's where we talk more about the two types of IP address, uh, which are the public IP address and then the private IP addresses. Usually, private addresses are handled for internal routing, and for external routing, they more or less needs to be converted to public IP addresses. Generally, public IP addresses are the only routable addresses on a given network. Uh, Private IP addresses are generally not routable, but for internal, forwarding, store and forwarding, they play a key role. But when it comes to external uh, information transmission out of a given network, then public IPs are the considered routable address. We'll get into all of that later on when it comes to subnettings and what have you. Okay, so yes, as I was saying, physical addresses will change from hop to hop, whereas the logical addresses usually remains the same. Great. So this will probably end the third session of the um, layering stacks that we have. Okay. So and the reading material is still revolving around the same chapter, chapter 2. So please do a read up on it to get a lot more information. If there are certain things that you didn't get quite clear, by going through the textbook, you can pretty much get a good understanding, or you can also, read some other supplementary materials or documents online as well. Okay, so that should probably do it for this lecture.